Welcome to the lesson on theorems of triangle congruence. In this lesson, we will discuss a few theorems that can help us prove that triangles are congruent. Now, recall that when we talk about triangles being congruent, we specifically mean that all the corresponding parts of these triangles are congruent. So every side is congruent to the corresponding side, every angle is congruent to the corresponding angle, and in that case, the two triangles would themselves be congruent. Now, certain theorems allow us to prove that triangles are congruent without having to involve every single part. That means we wouldn't have to know about each side being congruent to its corresponding or each angle. So what would those theorems be? Would I have enough by saying that this angle is congruent to this angle and this side to this side? What specifically do I need to know in order to show that triangles are congruent? The first theorem we can discuss is called the side-side-side triangle congruence theorem. Now that would state that if I know if the three sides of one triangle are congruent to the corresponding three sides of another, then the triangles are congruent. So all I would have to know is to have matching side lengths. As we can see, AC is congruent to AC prime, BC to BC prime, and in this case, those triangles end up being congruent. This theorem comes from the principle that there's only one way to make a triangle with three given side lengths. You can try this out on your own time. Try making a triangle with the side lengths 3, 4, and 5. So let's say centimeters to keep it easy. Now you can try and draw it and see that you might not be able to match them, or you might not be able to close a triangle. But if you keep working at it, you'll see that you'll be able to make a triangle of 3, 4, 5 that looks a lot like this. You might make it another way and it looks a little bit different. Or another one that looks like it's maybe slanted. But at the end of the day, they are all indeed the same exact triangle with the same exact side lengths. Those side lengths are bound to one triangle shape. The next theorem we talk about is called side angle side. With side angle side, we specifically look of two sides and the included angle of a triangle being congruent to the corresponding sides and the included angle of another triangle, then we can conclude that those triangles are congruent. Now, if we look at the two examples to the left of this definition, we notice that we do have this side matching up with a double dash and a single dash here. And then, of course, as I put a box around the angles, we can conclude that those triangles are congruent with side angle side. In this example, however, I do have the two pairs of matching sides, but there's a discrepancy here with my angle. It should be in a different location, so these are not congruent. The angle must be between those sides. With the angle not being between the sides, I can't show congruence. Let's take a look at another example where we can use side angle side. In this specific case, we know of one pair of congruent sides and then two corner angles. However, the side that these two triangles share, being congruent to itself, would be enough to show me side angle side. And the side can be shown to be congruent to itself with the reflexive property of equality. The next theorem we discuss is called angle side angle. Now the slight difference with this theorem is that we talk about two angles and an included side of one triangle are congruent to the corresponding angles and included side of another triangle. That would make the triangles congruent. So again, I can match up the two pairs of angles and notice the side that is between those angles. With angle side angle, we have enough to prove those triangles are congruent without having to go any further. Now this theorem kind of finds its basis from the triangle sum theorem. Now remember, the triangle sum theorem states that any three angles of a triangle, let's say ABC, would add up to 180 degrees. Now that's every triangle. So if there are two triangles that we're thinking about, two triangles in question, if I have A and I have B, well, C must take us to 180. So if with the other triangle, if A is congruent to D and B to E, D and E's sum has to be the same, meaning that C must be equal F. So even without knowing that third angle, two angles would suffice. The side in between guarantees that we'll get the exact same shape. So let's do a little bit of practice. Let's look at these three pairs of triangles and see if they are congruent, and if they're congruent by what theorem. So looking at this first one, I can draw some parallels, and I can write these down to see what I ultimately have. I do have a pair of sides. I identified a second pair of sides. And then I have an angle. So I have SS and A. Now I gotta look, that angle is in between my sides. So I have side angle side, and these two triangles are indeed congruent. Second, I look again, I have two pairs of sides, but my angle is not in between. So even though I have SAS, by what I have, these are not congruent because that angle not being in between states that I would have SSA if I follow the order. So I do not have congruence here. SSA, or side-side angle, is not a theorem. In my last example, I can match up three pairs of congruent sides to give me side-side-side congruence.